I am the eclectic doctor. My interests are various, and where they intersect is where I love to be. This series is inspired by my students at Algonquin College, many of whom are just starting out in the world of programming. This series is inspired by a particular problem my students were running into. Basically, they were getting so overwhelmed with the details of different languages and programming environments that they were losing sight of the simple beauty and pleasure of programming. In this series, I intend to present, in a language and platform agnostic way, the fundamentals of programming that are common to most of what we call imperative, that is, command or instruction-based programming. These fundamentals are usually what students fall in love with early on, only to have the complexities of development sap away the energy of that love. Here we will look at the trees so that when we enter the forest, we know at least one place where things will make sense. The problem with computers is that they are everywhere today. Heck, I even have one friend with a Wi-Fi enabled toaster. Yep, that's a computer too. In a world inundated with computers, it behooves us to at least know a bit about how to make them work for us. So let's define the computer. The computer is a machine, usually a digital device, that has the capacity to remember and follow simple sets of instructions to accomplish various tasks. This was the vision that goes back to the Manhattan Project mathematician John von Neumann, a computer that can work on data by following a set of instructions and thereby accomplish a lot of the tasks that are really tedious for us to do by hand. Without digging into the nuts and bolts of how the computer does all this, what I want us to understand is that the computer follows those instructions religiously. Computers do exactly what we tell them to do in exactly the order we tell them to do those things. And I know there are times when we can become convinced that computers have a mind of their own and are bent on frustrating our plans. But the simple fact is that if the computer is doing something, then it is because that is what we asked it to do. Rare is a situation where this is not the case. But that raises a problem. How can we tell the computer what we want it to do in a way that the computer will understand? The computer will never really assume what you mean. Computers are literalists. Armed with this understanding, we can now define the computer program as an ordered set of instructions that we ask the computer to follow. This is a simple program. Yeah, I know I chose a harder language to start us off, but this is the classic program that I always write in every language that I work with. It's simple. It tells the computer to print the words "Hello World" on the screen, and then it ends. Now, just a heads up, all of the code I use in this course will be available in a GitHub repository that's located at the link on the screen. You can simply visit that link and take a look, and I'll explain how to navigate the repository in a later talk. I'll post a link in the comments below this video. Apart from a few cryptic lines of code, here the instructions are fairly simple. Print the "Hello World" message on the screen, and then return to the terminal's prompt. The computer program is a simple set of instructions, written in a way that can be translated for the computer to understand. These computer programs are written in programming languages. Those are special languages that allow us to write instructions for the computer to execute in something that is at least somewhat readable for us humans. And I should say, predominantly us Western English-speaking humans. We're talking about two kinds of languages: high-level languages and low-level languages. Where a high-level language requires more translation into the instructions that the computer knows, these high-level languages are more English-like, although one could argue that their limited syntax makes them sound like incomplete sentences most of the time. Now, low-level languages are closer to the actual instructions that the computer knows how to execute. And really, the computer can only carry out very simple instructions, but it can do this so fast that it feels like the computer is actually doing a lot of thinking on its own. So a fun fact is that the lowest form of computer language that is at all human readable is assembly language, which generally has a one-to-one relationship between commands typed in and instructions the computer executes. Our little "Hello World" program can be written in about 15 lines of ARM assembly, provided we use a printing routine provided by the operating system. If not, then it takes us a lot more lines of code. What is cool about this is that no matter how high or how low a language is, there are ways to do all of the programming chops that we will cover in this series. This is the heart of the programming language. It lets us write in step form instructions for the computer to follow, and the computer will dutifully follow those steps. And if we are careful putting those steps in just the right order, the computer will follow our instructions and we can pretty much make them do anything that we can imagine. After all, this was the allure that drew me into programming as a youth, when I was at computer camps at the local teachers' college, working on those pet computers and just fascinated at the endless possibilities that were ahead of me. Now, I really like playing board games. And one of the things that you find with almost every board game is a rule book. And in that rule book, there are usually instructions for setting up the game so that you can play it. The image shows one of my favorite two-player games, Jaipur. In order to set it up, you need to put 3 camel cards face up on the table between the players. Then you shuffle the rest of the cards, dealing each player a hand of 5 cards. The remaining cards are placed face down in a stack, and then you deal out the top 2 cards next to the camels. And so on, you follow these instructions until all the tokens are organized in a marketplace and the game can begin. The point is that even the most complex game can be set up following a set of instructions that are usually given to us in an order. So there's usually an order and a reason why those things are done in that order. After a while, I'm going to remember most of the setup, and I'll just need these steps as a guide to make sure I do not forget anything. This is the part a computer cannot do. It cannot improvise or deviate from the order of the instructions it is following. Really, the only thing that can stop it is if an order makes no sense to the computer. And in that case, most computer languages just stop working and likely throw some sort of error message. Remember that by definition, a computer is a machine that can take a saved list of steps and execute them one at a time in the order they are given to the computer. It would be great if all we had to do was to type in the steps and give them to the computer. This is often the part where students become discouraged. We're going to just kind of break it up so you can see the different parts that are here. These are the basic parts of code. Programming languages allow you to write comments to help you remember what it is your code does. And we'll talk about this more in the programming chops section. The thing to note is that most of the time, the computer just ignores these lines. There are usually instructions for the translator that turns our program into something that the computer can follow. And we'll talk about these more in the development paradigms section. But what I want to focus on the most is the steps of our program. Typically, our steps are put into a block of code. In this case, it is the main block of code for our program. Some languages use words like begin and end to identify a block of code. Most modern languages use squiggly brackets, like the C language here, which is why we can say that most modern languages are C-like. There are even languages that simply use indentation to identify blocks of instructions. The thing to note is that inside the block are the specific steps we want the computer to perform. 1. Print hello world on the screen. 2. Return to wherever this program was run from. If you have a strong foundation with building the steps, then you can focus on setting up your environment or language for whatever you are working with and keep the instruction writing as a separate task. It is usually the more enjoyable task, making the setup worth the effort. What we'll do in this series is focus on the common foundation of writing these steps, what I call the programming chops, so that when you end up working on a development project in a completely new environment and with a new language, you know that the new things that you'll have to learn are really just setting up your tools. The new language will have its idiosyncrasies, of course, but the same logic will be there. You just might need to write it with different punctuation or formatting, but all languages will allow you to ask questions of data, loop through blocks of code, and even save your data. To sum up, you can now say that programming is simply creating steps for a computer to follow. In our next session, we'll talk about how we break up a problem into steps that we can readily write out into a programming language.